Okay, in the last video, I presented that corollary to a previous theorem that essentially says, hey, if you reduce everything modulo m and then start doing adding and multiplication, it all still works, right? So we're going to take that idea and apply it. So we're going to look at something called arithmetic modulo m. And first, what we're going to do is introduce a little bit of new notation for something called integers mod m, where m would be some specified number. So like integers mod 10, or integers mod 12, integers mod 36, or whatever. And the notation is to write the symbol for the set of integers and then put a little subscript m. And that is a set, which is essentially the set of all the congruence classes. It's technically like what it is. It's like those congruence classes, like set of all things that are congruent to each other, mod m. But then we just take the a representative of each congruence class, and the representative we pick is usually the small one, the smallest one. That's not negative. So this is generally represented as the set of numbers starting from 0 and going up to m minus 1. It's not going to include m because it loops back around. As soon as you get to m is congruent to 0, right? Mod m is congruent to 0 because you can subtract it and get, a multiple of m. M would be itself a multiple of m, so it goes back. So it's kind of like if you took the entire set of integers and you wrapped it into a circle, right? It's kind of like here's a circle. We took all the integers and we went 0, 1, 2, 3, 4, 5, 6, and then 7 is going to be the same as 0, and then 8, 9, 10, 11, 12, 13, and then 14 is going to be the same as 7 and 0, and then 15 and 16 and 17 and 18 and 19 and 12 and 20, and then 21 and so on. So it's like kind of like you wrap everything around and then you forget about all of that. You forget about all those numbers except for the smallest one, the remainders that you would get if you divided by 7. So this right here is like a little picture of z mod 7. Okay, it's like the entire infinite set of integers wrapped up so that it loops around over itself infinitely many times, and you just basically boil it down to 0 through 6, and that's it. So that is the idea of integers modulo some number. And within that set, you can then define an addition operation on that set and a multiplication operation on that set. And those are going to be, and the set is going to be closed under those operations because of that corollary in the last video. Okay, so we can define addition and multiplication. And in the textbook, you'll see a little subscript m that comes after these things, like that. But when the context is clear, that little subscript m is sometimes omitted. So I'm usually not going to bother writing it. So we're going to define them, though, by a plus b within this set z mod m is going to be equal to whatever you get by adding a plus b in the normal sense, but then reduced mod m. Okay. And multiplication, the same way. A times b is going to be the same as taking a times b in the regular sense and then saying mod m. So these are the special operations we're defining. The plus mod m and the times mod m are the special operations we're defining like this, like that, and like that. And they are going to be things that you can do on this set, and this set's going to be closed under those operations, just like how integers are usually closed under addition and multiplication. So let's just go through an example. Let's look at z mod 5. That's just going to equal the set 0, 1, 2, 3, 4. That's z mod 5. And now any addition or multiplication that we do within this set, it's going to loop back around on itself. So like, for example, 2 plus 3 is 5, right? Except 5 reduced modulo 5 is actually 0. So within this set, with these new operations we've defined on it, 2 plus 3 equals 0. And 3 plus 3, for example, is 6 normally, right? Except if you reduce mod 5, it's 1. So 3 plus 3 is 1. If we do like 3 times 4 is 12, but reduce mod 5, is 2, right? 2 times 4 is 8, but reduce mod 5 is 3, and so on. That kind of thing. So properties that this will have, like I mentioned, it's going to be, Z mod M is going to be closed under addition and multiplication. So that's nice. Within that set with those operations defined on it, it's going to be commutative. All those operations, both of those operations are going to be commutative and associative. And it turns out also the distributive law is going to work with addition and multiplication on that set. So all those 3 laws are going to work. You're still going to have this additive identity of 0. So it's still the case that when you add 0, it doesn't do anything, right? Adding 0 has no effect on something. And likewise, you're still going to have the multiplicative identity, which is 1, right? Multiplying by 1 still has the effect of doing nothing. So those properties still hold. But here's one thing that makes it very different. You do always have what are called additive inverses. And an additive inverse usually is an opposite, like the additive inverse of 6 in the regular integer realm is -6, right? Like, so with regular math, as you've learned it before, 6 plus -6 is 0. So those are the additive inverses. They're called opposites. But in the realm of integers mod m, right, which is sort of like a different world with some different new operations that are defined, right, that I've never seen before. In this different world, additive inverses do exist for every number, except it's not negatives, because there are no negatives in this world, right? You only have numbers 0 through m-1. So there's no such thing as a negative number in here. But you can reduce or kind of like simplify those negative numbers modulo m. And so you do have additive inverses, but they look different. So like in this example, up here in Z mod 5, as we saw here, because 2 plus 3 equals 0, it's just like 2 plus -2 equals 0, right? In fact, -2 and 3 are congruent to one another, as you may remember from a previous video when I was talking about all the things that are congruent to 3 mod 5. So 2 and 3 are opposites, so to speak, in that world. Now, I will just mention one other thing here, which is that while additive inverses are guaranteed to exist for every number, multiplicative inverses are not guaranteed to exist for every number. In fact, multiplicative inverses sometimes exist for some numbers, but sometimes they don't. And whether or not a multiplicative inverse exists is actually a bit complicated, and it has to do with some stuff we're going to get to in a later section called relatively prime, and it has to do with greatest common divisor. And I don't really think that subject of the existence or non-existence of multiplicative inverses in Z mod M, that's not really within the scope of this course at all. So I'll just say, if you think this is pretty cool and you're interested in this idea of like, ooh, how can we define operations and then study the algebraic properties like within a different set that's not the regular number system we usually use. If you're interested in that, take a class called Abstract Algebra, and you will have a ball, my friend. I totally loved that class when I took it in college, and so as you can see, I'm kind of enjoying introducing you to some of these ideas. So that's it. That's it for 4.1.